Okay, so our first homework from Unit 4, or Getting Ready 1, we are going to start here with reviewing the distributive property. Okay, so remember, distributive property is A times quantity B plus C is equal to, now you distribute the A to both terms inside the parentheses, that becomes AB plus AC. So these first two should definitely just be review. 3 times 2x is 6x. 3 times 7 is 21. You can do nothing else with that. It's simplified completely because there are no like terms there. Negative 12 times 5x, negative 60x. And negative 12 times negative 4, so you use the signs in front of each term. Negative 12 times negative 4 is positive 48. Okay, now these are really, these last 5 problems are really the reason why we're doing distributive property again, is to practice or remind ourselves how we deal with variables times other variables. So 5a times negative 3a. The 5 times negative 3 is negative 15, but then you're also multiplying a times a, which is a to the second power. Okay, then when you distribute 5a to 13, 5 times 13 is positive 65, and then you just bring the a along. These two terms are not like terms. This one has a squared, this one has just an a, which is to the first power. So you cannot do anything else with that. That cannot be simplified any further. Number 4, 9x times 6x, we've got 54x to the second. And then 9x times negative 2 is negative 18x. Number 5, don't let the fraction get you nervous. You still treat it like any other coefficient out there. So I'm really doing 2/3 times 12. So 2/3 times 12, this is actually 12 over 1. So 2 times 12 is 24. 3 times 1 is 3. And 24/3 is 8. So 2/3 times 12 is 8. And then we're multiplying x times another x is x to the second. Now 2/3 x times 18, I'm going to do 2/3 times 18. Again, this means 18 over 1. So 2 times 18, 36. 3 times 1 is 3. That reduces to 12. So 2/3 times 18 is positive 12, and then you got to bring the x along with that term. Just like before, not like terms. X squared and x are not alike. Okay. Distributing 4/5 a. Well, come down here, 4/5 times 10 over 1, that's 40 over 5, which is 8. So we have 8, and then a times a is a squared. And we're going to do 4/5 times, now that's a negative 25 actually. So a positive times a negative is negative. And now I don't have to worry about the sign anymore. I can just come down here with 25 over 1. So 4 times 25 is 100. 5 times 1 is 5. So that gives us 20. It's minus 20. And now a with this term times b with the negative 25, that becomes ab. Remember, you do not have to have terms be alike, have the same matching letters in order to multiply. You can multiply anything. It's only adding and subtracting that you deal with like terms. So these, again, are not alike because the variable parts don't match. This is a squared, this is ab. And last one, negative 4/11 times 121x. Well, a negative times a positive, I know that first term is going to be negative, so I can just treat it now like 4/11 times 121. Now, you could do 4 times 121 and get 484 over 11, but if you can remember what your elementary school or 6th grade teacher taught you about simplifying these, since 11 goes into 121, I can cancel this 11 and reduce that one to just an 11. So this becomes 4 times 11 is 44 over 1, or just 44. Now multiplying x times x makes x squared. And then let's distribute negative 4/11 times 22. And we'll take care of the sign first. Negative times positive is negative. And let's come down here with 4/11 times 22 over 1. Now, you can do that little shortcut again, like we did above. I usually don't bother when it's small numbers like this, but just for the practice, since 11 goes into 22, I can cross this one out, make that one a 2. 4 times 2 is 8. 1 times 1 is 1. 8 over 1 is 8. And since this 4/11 had an x, the 22 did not have a variable, it's just x. All right, so we're going to look at sets of 3 functions. In each one of those sets, one will be linear, one will be exponential. We should be really, really familiar with picking those out. The third one, whatever one remains, is some new kind of function. Well, it's going to be quadratic. Okay, so here's the word written since it's new to you. That third one, the one you don't recognize, the one that's neither linear nor exponential, will be a quadratic function. So what we're doing is we're looking for what are some of the characteristics that we notice with these quadratic ones. And we can try to make explicit and recursive formulas for the new one, even though you don't really have a method identified in your head. So let's go through and first, with A, B, and C here, find which one's linear and which one's exponential. Those are the two that are most familiar to us. So the pattern that I see in box A here, from 128 to 256 to 512 to 1024, is it's multiplying by 2. That makes this one the exponential. We know that it has a common ratio. In this case, it's 2. All right, we'll come back and do the formulas in a bit. This one, from 49 to 64 to 81. Now, I don't notice anything. I can't multiply some nice, neat little number and turn 49 into 64 and then 64 into 81 and so on. So I really have to do a check if we're going to look for exponential. But since we know only one of the 3 can be exponential, that's out. This could be linear or this new type called quadratic. So is it linear? Well, that goes up 15, then this goes up 17, so no, it's not linear. It doesn't have a constant rate of change. This must be our new one, which we're terming quadratic. We don't really know any characteristics there yet. We will come back and deal with that. And C then must be a linear one. Let's verify that. This goes up 2, up another 2, another 2, another 2. So yes, this one is linear. And we recognize it has a constant rate of change, which again is 2. So let's do the explicit and recursive equations for the 2 functions that you have already studied, that you're familiar with. For exponential, our explicit formula has to take the form y equals a times b to the x. So they actually called it f of x up here, so I'll stick with that. F of x is equal to, now the a represents what we have called the 0th term, the y-intercept. Now that is certainly not shown in this table. It starts with the 7th term, so I'm going to have to go back all the way to the 0th term. That means I'm going to have to go in reverse for this pattern. So instead of multiplying by 2, I'm going to need to divide by 2 over and over and over. So until I get all the way to the 0th term. So if I divide by 2 once, I'm at 64. Do it again, I would be at 32. Again, 16. Again, 8, 4, 2, and 1. So we did all that work just to find out that the 0th term is 1. Our multiplier is 2 to the x. The recursive formula, remember those have two parts, so we'd have to start with something like f of 7 is equal to 128, and then my formula, f of x equals f of x minus 1, and then the pattern is that it multiplies by 2. For our linear one over here at C, in this one, our explicit formula will take the form y equals mx plus b. So f of x equals constant rate of change, 2, times x. Now for that 0th term, I can do something similar to what I did in part A there with the exponential. I can just subtract 2, subtract 2, subtract 2 until I get to the 0th term. But we actually had another method for this. If you recall, we could substitute into y equals mx plus b everything that we know. So we know the m is 2. We could take any one point, I'll take this first one, 713, and substitute that for x and y, and solve for b. So 13 is equal to 14 plus b. Subtract 14, so b is equal to negative 1, minus 1. The recursive formula, two parts again. So f of 7 equals 13. And then f of x equals f of x minus 1, and our pattern is to add 2. All right, now let's jump in and see what we can discover about this new function, which we're calling quadratic. Well, remember we had said up here when we were looking for linear that this added 15, this added 17, this adds 19, this adds 21. Now remember, it was not linear because these differences were not constant. But if you look at what kind of pattern they do have, those differences, those numbers I wrote in blue, actually have a pattern themselves. They are increasing 2 at a time. So one of the things that's important to recognize about quadratics is that what we're going to call the first differences, all right, which means at the results of subtracting each successive y term, the first differences are linear. First differences, linear. That is a linear pattern. The first differences have a constant rate of change. That y values don't, but the differences do. And what that means, if we think about what linear really means, is there is a constant rate of change, but it's like at this next step. From 15 to 17 is up to 17 to 19, and 19 to 21. And these would be called the second differences. So the first differences are linear. The second differences are where you'll see the constant. An explicit formula, we're usually going to do that using the calculator. There's a feature called quadratic that will take care of that. This one happens to be simple enough. If we look at how 7 turns into 49, and 8 turns into 64, and 9 into 81, this one is simply f of x equals the x term, the x value, squared. Now the recursive formula will never be something you enjoy doing here for a quadratic function. So we have to start, just like we always do, with a beginning, like f of 7 equals 49. We still start the formula part by saying f of x equals f of x minus 1. But here's where it gets a little tricky. We don't just add the same number every time. We don't just multiply by the same number every time. What we are adding is actually a linear pattern itself. So we are going to add, and what you will put after that f of x minus 1 is the linear formula, the mx plus b, that represents these numbers 15, 17, 19, 21. Okay, so what's the formula for those? Well, the constant rate of change in this first difference column is 2, so plus 2x. And then the easiest way I can tell you to do the b for it is to just adjust. Try a number and adjust. So here's what I mean. If we tried looking at how this formula gets us from the 7th term to the 8th term, okay, from 7th to 8th, that would mean if I were looking to do f of 8, I would take the f of 7 answer, okay, that was 49, plus, this is doing f of 8 would be the previous value, f of 7 is 49, plus 2 times the 8. Well, 49 plus, this is 16. 49 plus 16 doesn't get me to 64. 49 plus 16 brings me to 65. That's too big by 1. So this 2x needs a minus 1 to trail it. Let me do that one more time with another value. This time, let's say we're going to go, and I'm randomly just picking these out of nowhere. If I wanted to go from 9 to 10, okay, then I'm saying to find f of 10, I go back to the value of f of 9. Well, the value of f of 9 is 81. So 81 plus 2 times my x value is 10. 81 plus 20 would put me at 101. Well, that's 1 bigger than I need it to be. So again, I need to subtract 1. All right, and we will practice that a bunch, but I realize it's a little difficult the first time you see it. All right, we have another row of 3 functions, one of each kind. So do you notice the linear and exponential as soon as you look at them? Well, let's see. From negative 17 to negative 12 goes up 5. Negative 12 to negative 7 is up 5. So this one is our linear because it has a constant rate of change. From 1/25 to 1/5, you might not know right away how that changed. From 1/5 to 1, you might not recognize. But from 1 to 5 multiplies by 5. From 5 to 25 multiplies by 5. And then when I see what I believe the pattern to be and check it with these, it does hold. If you multiply 1/25 by 5, you get 5/25. That reduces to 1/5. 1/5 times 5 is exactly 1 whole. So this is our exponential, and it's because it has a common ratio. Well, we know then that that leaves us box F to be our quadratic. Let's see if we can notice those 2 characteristics I pointed out up above. And that would mean looking at our first and second differences. Okay, so from 9 to 6 goes down 3. From 6 to 5 goes down 1. From 5 to 6 goes up 1. From 6 to 9, up 3. If I look into those numbers at the next level, from negative 3 to negative 1 is up 2, up 2, up 2. So there I see it. I see that my first differences form a linear pattern. Negative 3, negative 1, 1, 3, and that my second differences are constant. Now that's really 2 ways to say the exact same thing. If I say the first differences are linear, well then that could only be true if the second differences are a constant, and vice versa. If I say my second differences are constant, that would imply the first differences are linear. So you don't need to say both of these when you are justifying that a function is quadratic. Go back into our formulas. For the linear, I'm going to have f of x is equal to the constant rate of change times x, and then plus the 0th term. Well, it's negative 7. For recursion formula, I would say f of negative 2 is negative 17. And then to get any new f of x value, you go to your last one and you add 5. For the exponential one, f of x is equal to 0th term, which is 1, times the multiplier, 5, to the x. The recursive, f of negative 2 is 1/25th. And to get any new f of x, we go to our last term and we multiply it by 5. For the quadratic, okay, the formula, which again, I will just give this to you because we're going to get it from the calculator using quadratic, and you can just verify that it works. The formula f of x is the result this time of squaring the x value and then adding a constant of 5. So negative 2 squared is 4 plus 5. Negative 1 squared is 1 plus 5. 0 squared, 0 plus 5. 1 squared is 1 plus 5. The recursion one, okay? So you can start learning this one, calculator or not. F of negative 2 is 9. Any new term is the result of going back to your last one and adding. Now, what do we add? It's that constant second difference times x, and then we need to try to see if it needs adjusted. So if I'm trying to go from the 0th to the 1st, I would avoid these negatives just because negatives can throw you off more simply than positives. If I were going from 0 to 1st, that's f of 1 would be the value of f of 0, so 5, plus 2 times the 1. Well, 5 plus 2 times 1, that's 7. Do I want f of 1 to be 7? No, I want it to be 6. So once again, just like above, I need to subtract 1. Right? If I subtract 1, that 7 will be the correct value. Now, I'll show you that one more time if we didn't have the minus 1 yet. If I wanted to go from 1st to 2nd, that would mean I'm trying to find f of 2 by looking back at the value f of 1, that was 6, and adding 2 times 2. 2 times 2 is 4. 6 plus 4 is 10. Well, I don't want f of 2 to be 10. I need it to be 9. So how do I make it 9? I need a minus 1 after all of that. So my recursion formula is the f of x equals f of x minus 1 plus, and then a linear formula, 2x minus 1. All right, on the next page, it asks us to graph the 6 functions from the last problem, the 6 we just looked at, linear, exponential, and quadratic. This is important here that you place your axes so that you can show all 5 points. You need to tell me, show me, somehow identify your scale. Okay. Now it asks for the explicit formula for each one. We already wrote those, so we can just recopy them at the top. Like this table for A, which was an exponential one, the formula was f of x equals 1 times 2 to the x. So if I need to plot these 5 points on the graph, my job here, what I'm really practicing is identifying a scale that'll work. So there are 20 boxes, it's 20 tall and 20 wide, I believe, 2, 4, 6, 8. Yes, 20. So if I have 20 boxes to get myself to 2,048, just can't quite count by 100s. It won't make it. But if I do by 150 or 200s, I can definitely make it. Okay? So count by 120s, 125, 150, 200. Any of those would work. So I'm going to put my axes right along the edge. That's even a decision that you might not make for a problem later in this number 9. And we need to make sure that we are numbering our scales. The x's can be 1, 2, 3, 4, 5, up to to 11 at least. If I need to count here by 125s, I need 7 128, 8 256, 9 512, 10 1024, and 11 2048. And this is not a scenario problem. It doesn't have some special meaning that I need to be aware of. So I'm going to go ahead and connect that as a continuous curve. But I had to show the 5 points in the table. All right, in part B, I'm going to have to get up to 121. Again, I have 20 boxes to do it. I can count by tens. I don't need any negatives. So again, I can locate my axes right at the edge if I choose to. I'll count by ones on the x-axis. The y scale, I said I was going to use tens. 7, 49, 8, 64, 9, 81, 10, 100, and 11, 121. Now, you don't really have any expectation at this point of what that should look like. It's going to be called a parabola. This formula is f of x equals x squared. It's going to be called a parabola, so you don't have to bother connecting those. Again, you don't really know what else should show up there. It is not a line. Your scale may make it appear linear. It is not. And part C was our linear one, where we had a formula f of x equals 2x minus 1. All right, I need to get to 21, so I just missed being able to count by twos. I'm going to need to count, or by ones, I'm going to need to count by twos. So we will locate our axes on the edge. Once again, we don't need, well, that's not true. If we graphed here to the y-intercept, we do have a negative number. So let's not locate those. Let's give a little space for a little bit of negatives. Okay. So in this case, I can still number my x's by ones, but I need every box to represent twos going up. Plotting points. 7, 13. So here would be 12, 13, 8, 15, 9, 17, 10, 19, and 11, 21. This one, we do know a lot about it. We know where the y-intercept would be. I know how to fill in those other missing points that are not in the table. So I can go ahead and connect this one with a line. It would be linear. So, oops, wrong line. All right, and we'll do it all over again for D, E, and F. Part D is going to be our linear one from this row of functions. And our formula was f of x equals 5x minus 7. Now, I'm not saying it's worth your time to plan this out and make the scale the same as I'm going to, but since my y values go from -17 to 3, that's a span of 20. That's exactly the number of boxes I have. So if I wanted to, if I planned it just right, I could make my x-axis here which leaves me 17 boxes below the x-axis for negative 17, 3 above for positive 3. Okay, so let me go ahead and number that while I'm thinking about it. I don't want the y-axis right on the edge of the box either, because I know I have x's from negative 2 to 2. So I need to allow to graph a couple of negatives. Now, as long as you leave at least 2 boxes to the left of the y-axis, you can locate it anywhere. I'm going to put mine about here, and I'm counting by ones on that axis. So this would be negative 4, 3, 2, 1. Here is the point 0, 0 at the origin. 2, 4, 6, 8, 10, 12, so on. That will allow me to see all of these points as neatly, as accurately as possible. So negative 2 was negative 17. Negative 1 is negative 12. 0, negative 7. 1, negative 2. And 2, positive 3. And just like we expected, hoped, and needed, we have a linear pattern there. This is a line. I can draw in a solid line to connect those, since this doesn't represent any certain scenario. Okay, E, our formula for our exponential function we had there was f of x equals, the 0th term was 1 times 5 to the x. And it looks like something happened to my little box here. And I can't see, okay, I can't see that last number there. It was 225 is what that last point here was, 225. So let me, 225. All right, so if I need to get up to 25 as a y value, I cannot count by ones. I'll need to count by at least 2s again. 2 seems like a good choice to me. So 2s on the y-axis vertically, 1s for the x's. Again, I cannot, I can put my y-axis right on the edge. I can't put my x-axis on the edge. That was backwards. I can't put my y-axis on the edge. I can put the x-axis at the very bottom. I think I said it correctly that time. Because I need to be able to show the x value negative 2. All right, so I'm going to count by 1s on the x-axis and the y-axis by 2s. Points, here we go. Negative 2, 1/25. Negative 1, 1/5. 0, 1. 1 is 5, and 2, the one that I lost somehow there, was 25. All right, we know this is an exponential curve, not representing any known scenario, so we know to extend our curve in a continuous fashion, just so. And finally, the other new quadratic one, which was, if I remember here, let's see if I can, it was f of x equals x squared plus 5. Right? Now our values this time only go up to 9. So my y scale for one of the few times can be 1s. I can count by 1s. But I do still need to show at least a couple boxes into the negatives on the x-axis. So I can count by 1s on everything. Everything can be counting by 1s. And these points should make a curve. It should not be linear. Negative 2 is at 9. Negative 1 is at 6. 0 is at 5. Now notice the symmetry. That could be another characteristic that we added up on the previous page. There will be symmetry in every one of these parabolas that we see. All right, and this last page, we are looking at, they just refer to it rate of change, but in every case, these are linear functions, so it's a linear rate of change, a constant rate of change. So we'll find that in different ways. For number 10, since we have a graph, the simplest way is to identify 2 points. I'm going to pick those two. I can see exactly where they are, and count rise over run. So from -3, I go up 1, 2, 3, 4, and I run 1. 4 over 1, or 4. That is a positive slope because the line is increasing. Number 11, I got another graph. This one, though, is a decreasing one, so I should expect a negative slope. I'm identifying 1, 2 points. You also could have used this one at 1, -2. This time, I will again do rise over run. But since I count 1, 2, 3 down, my rise is -3, divided by +1, which is -3. Number 12, now I don't have a graph, so I'm not looking for rise over run. I just need to identify any 2 points. I might as well choose the first 2. And I can use that slope formula. So if I put 68 minus 65 for the y differences, then I need to do 26 minus 25 for the difference in the x's. That's 3 over 1, or 3. 13, another graph, count another rise over run. So I've got a point here at -5, 0. I've got a point here at 0, 2. So rising over running, I'm going up 1, 2, and I'm going to the right 1, 2, 3, 4, 5. My slope is 2/5. All right, since we are looking at the recursive formula, the rate of change is built in. It's right here. This formula tells us to get each new term, you go back to your last one and add 5 to it. So my rate of change, my slope, is just 5. 15. So in a word problem, we need to somehow pick out either a stated rate of change, or if we're not lucky enough for that, then we need to identify 2 points so we can find our rate of change with the formula. So George weighs 210. He's loaded 15 boxes onto the elevator, and each box weighs 50. Identify the rate of change. So this is a whole problem that we could solve and figure out how many boxes George could load with him, but it's not asking us for that. All we need is the rate of change. So what's changing in this problem? Well, the unknown is how many boxes the elevator can hold. It's changing at 50 pounds each time we add or subtract a box. So this would be 50 pounds per box is our rate of change. That's what's changing. All right, 16 specifically asks us for the slope and just provides 2 points. So we're going to use our formula again, y2 minus y1 over x2 minus x1. So the two y values are 12 and -16. Think of them any order you want. If I decide to do -16 minus 12, though, then I have to follow that up with the x's in the same order. I would have to do -11. Since I started with -16 on top, I have to start with -11 underneath, minus, now this is a -3, so there's a minus for the formula, and a negative with the 3, so there's double negatives there. This becomes -28 in the numerator. Now in the denominator, when you have 2 negatives, it's like adding. So -11 plus 3 is -8. Each of those can be divided by 4, so we have 7 halves, and negative over negative cancels to make a positive 7 halves, or if you got 3.5, that's equally good. 17, got a table of values. So what I did in the table up above, one of the previous problems, was just plugged it into the slope formula. But you have another alternative with the tables, and that's just to look at delta y over delta x, as long as you know you pay attention to what the x's are counting by too. So here's what I mean. This goes up a half, up another half, up another half, and up another half. So does that all by itself make the rate of change 0.5? Well, almost. It would, and it does, as long as the x's are also counting by ones, or are counting by ones. Sometimes, though, they're not. Sometimes you have a random smattering of x and y values, so you would have to actually look at each delta y, in this case they're all 0.5, and divide it by its corresponding delta x. So in this case they're all 1. So yeah, my rate of change does turn out to be 0.5 or 1/2. But just be careful that your table is counting by a consistent measure before you jump to that conclusion. 18 gives me 2 function notation points, values, but really that is just points. This point, it's showing me in coordinate notation will be -4, 24. This one would be 6, -36. So what do we do when we have 2 points? We use that formula. Subtract your y values, divide that by the difference of the x values. So my y values are 24 and -36. I'm going to do them in just that order. 24 minus, and then this negative sign, -36. Then the denominator must start with the corresponding x, so -4 minus 6. Well, these two negatives become addition. 24 and 36 is 60. -4 minus 6 is -10. And 60 over -10 is -6.